Ridiculously weak. Example. Why are they so weak? Actually, 10 to the minus 11. That's why. Example, what's the force between two people 1 meter apart? She'll make a big leap. 100 kilograms each. What that is in pounds?
220 something?
Somewhere over 200 pounds. So these guys are football players. Force between two people, 100 kilogram people, 1 meter apart. So they're pretty close to each other too. What's the force of attraction, the gravitational attraction between them? F equals 6.67 times 10 to the minus 11. Whatever the units are. 100, the product of the masses, 100 divided by the distance apart, 1 meter, quantity squared. I see 1, 2, 3, 4 powers of 10 is going to knock this down from minus 11 to minus, or up I guess, to minus 7. So this is 6.67 times 10 to the minus 7 newtons. How big is that? Let's figure out what kind of a mass would have a weight of 6.67 times 10. That's probably an easy way to think about it. Suppose that m times g was 6.67 times 10 to the minus 7 newtons, and g is about 10. So this would be 6.67 times 10 to the minus 8 kilograms. So we're talking about the force between two big people pretty close together is comparable to the gravitational force downward of an object whose mass is 10 to the minus 8 kilograms. No, because the 10 is in the denominator. So it takes a minus 7 to lowers it down even more to minus 8. That's like, you know, the weight of a speck of dust or something like that. That's how strong the force of attraction between two big people is, pretty close together. That's just, I do that example, but super easy example, but just to reinforce the point, the gravitational forces are not just weak, they're unbelievably weak. You're never going to bind two atoms in chemistry to make a molecule using the gravitational attraction of those two molecules. And gravity is simply irrelevant to almost every kind of human endeavor, except the force of gravity holding you down here. Why is that large? That gravity holding you to the Earth happens to be large, not because gravity is intrinsically a strong force, it's intrinsically incredibly weak. It's that we happen to live on top of a huge pile of dirt. There's lots of stuff down there, the Earth. So one of the masses in question happens to be gigantic in that particular case, in the case of our attraction to the Earth. It is in fact only when either one or maybe both of the two masses in question are of astronomical size, only then that gravity plays any role whatsoever. So it plays a role in holding you to the Earth. It's irrelevant in dealing with things on the Earth. Their gravitational attraction to one another is just too small to be of any interest. It's too small to be of any interest in nuclear physics, atomic physics, or elementary particle physics. Gravity is just irrelevant. Chemistry, biology, except for the being held to the Earth, gravity is irrelevant to all of those. The one place that it does become very significant is in astronomical context. In fact, gravity dominates the universe at the large scale, even though it's irrelevant to the universe at the small scale.
So if we find the force here, we find weight, our weight.
Yeah.
So when we plug mass of Earth and our mass?
I'm going to do that at the end of the lecture. It's actually, there's a subtle point buried in there, but that's right. This is exactly what's responsible for your weight on the surface of the Earth. This mass is the mass of the Earth. This mass is your mass. Yeah, and we can calculate from there, and we will. We'll calculate what little g is. but as I say, there's a twist in that argument, so I like to leave that for the end rather than the beginning. Stick to the things that are simple at the beginning. Okay, gravitational field forces are in them at all. Okay, but in planetary context, you really will notice them. So planetary motion is in fact the classic application, the classic place that we notice gravity at work. I've got in the back of my mind the sun and the Earth going in its orbit around the sun once a year. But actually it could be any kind of planetary motion. It could be the moon going around the Earth, if you like, or an artificial Earth satellite going around the Earth, or some moon going around Saturn. I don't care. All of these cases, typically, by the way the motion is, the orbits are almost circular, close to circular. And I'm going to pretend, for the sake of argument today, that the orbits are perfectly circular. You can get a few exceptions. Pluto is quite non-circular orbit. And that makes the calculation enormously more complicated. You take a junior level course in mechanics, and there they will solve the more general problem of elliptical orbits. But for today, we'll pretend circular orbits. So, Earth, around sun, moon, around Earth, etc. That's what I have in mind. By the way, in all of those cases, it's the case that the central object, the sun, or the Earth, if it's the Earth-Moon system, is very, very heavy compared to the orbiting object. That also makes life a whole lot simpler, because that means that the heavy object at the center essentially just sits there, and the light object goes around it. Actually, as you probably know, they're both moving around a common center of mass, and the sun is wobbling ever so slightly as the Earth goes around. But it doesn't move very much because it's so much heavier than the Earth is. Likewise, when the moon goes around the Earth wobbles around. I don't know. Something like that. But in fact, the amount of motion that the Earth undergoes is minuscule compared to the moon. So assume central mass so heavy that it doesn't move at all. In that case, the analysis of planetary motion is very simple, and it's based on 3 observations. 1, the thing is going, the planet, the satellite is going in circular motion, so what's its acceleration? V squared over r. Going in a circle, so it's got centripetal acceleration, A equals V squared over r, where r is the radius of the orbit. Second, Newton's second law says if the thing is accelerating, there better be a force. Third, Newton's law of universal gravitation tells us what that force is. What's the chain that's pulling on the satellite? It's the force of gravity. F equals Gm, the mass of the central object. I'll call that capital M. The capital M means the big stationary one at the center, whatever it is. And the little m will be the lightweight, relatively lightweight planet, satellite going around. That divided by the square of the distance away they are. Those are the 3 ingredients from which all of planetary motion, at least for the case of a heavy central object and essentially circular orbits around it, all follows from those 3 observations. So let's put them together. What does it tell me? F, which is GMM over R squared, is equal to the mass of the satellite times its acceleration. Oh, wonderful. Yeah.
Side question.
So, the force of gravity, Gmm over r squared, is mass times the acceleration, but the acceleration is v squared over r, because it's going in a circle, v squared over r. There we are. Compare the first equation and the last. The little m's cancel out. Mass of the satellite cancels out from the two. The r's, one of the r's cancels out, and I get v squared is equal to Gm over r. I'm going to put a box around that, although it's no law of physics. It's not something that I would ever memorize. Why? Because this is one of those derivations that's simpler than the answer is. It's very easy to remember those, I think. What are the ingredients in planetary motion? Centripetal acceleration is going in a circle. F equals ma, the second law. What's the force? Force of gravity, universal law of gravitation. Put those together, and immediately emerges v squared equals Gm over r. What does that tell us? It tells us that the speed of a satellite going in a circular orbit of radius r about an object of capital mass capital M is fixed. You can't take a satellite around the Earth, say, I want to stick that out 10,000 miles out there, and I want it to be going at 60 miles an hour. I'm sorry, you're out of luck. There's only one velocity it can have if it's going in a circular orbit of a given radius around a given object, the Earth. A problem that you might want to fiddle with. I was thinking of putting this in the assignment, actually. You know about geosynchronous satellites that they use? So the geosynchronous satellite appears, from our point of view, just to hang in midair above the equator at a certain point. What's the point? It's actually orbiting around the Earth, but the period of that orbit is precisely 1 day, right? 24 hours. So the Earth is rotating at exactly the same rate that it's going around, so it seems to be above a particular point on the Earth. Well, put that in. Find out, you know what the velocity has got to be in order for it to make the entire circumference in 24 hours. Find out what radius that's got to be, and you can calculate how high up you better put it if you want it to be in a geosynchronous orbit. Well, that's just an example. I'm going to do a different example now of this, using the moon's orbit just as an example, but there are 100 examples that we could run of this. Actually, there was one point that I wanted to make before I get to this, because there was an interesting cancellation here. Actually, not just an interesting calculation, an incredible cancellation took place there. M, the mass of the satellite, canceled out completely. Why did that happen? Because the mass of the satellite, M, played two totally different roles in this calculation. First of all, M is a measure of inertia via Newton's second law. It tells you how hard it is to accelerate that object. So it's a measure of inertia. Secondly, M, same damn M, goes into the law of universal gravitation. It tells you how strongly two things attract each other. I don't know that there's any other example in all of physics. Purvis can probably jump on me for this, but I don't know of another example in all of physics where the same parameter occurs in two utterly distinct roles. Utterly distinct roles, having nothing a priori to do with one another at all. We call it the principle of equivalence, or the equivalence. I should start right. Note that M canceled out. That's not some minor little thing, that's astonishing. Why does it happen? Mass is two utterly independent roles, unless these can tell you about general relativity and
I'm
stuff.
just confused there. No, unless maybe inertia comes
Oh,
from
from,
gravity in the sense that the mass would not show inertia. You could apply 9 force and get huge. Never mind.
I do mine, but I'm going to pick up on that after I've scribbled a little bit. I should have been scribbling while I was talking about it. I got excited. Mass plays two utterly independent roles. We're going to modify that utterly in actually 2 ways in a way. Mass plays two utterly independent roles. One measures the inertia of an object via F equals ma. Newton's second law tells you how resistant the object is to acceleration. And secondly, it measures or determines the force of attraction via the law of universal gravitation. F equals g m m1 m2 over r squared. So m comes into physics in those two apparently completely unrelated ways. And when you put those two together here, it cancels out. But that's an astonishing thing, that the same number m plays those two different roles. An astonishing thing. It's called, this is where I broke off a minute ago, it's called the principle of inertia, the principle of equivalence. The principle of equivalence is the equivalence of gravitational mass and inertial mass. Which should, by all rights, have two completely different numbers. I tell you the inertial mass of this object, which tells you how resistant it is to acceleration, and I also tell you the gravitational mass of it, but you can have all different combinations of a big gravitational mass and a little inertial mass, or vice versa. That doesn't happen. They're always the same. Equivalence of gravitational and inertial. Einstein used the principle of equivalence as the cornerstone for the general theory of relativity, which is Einstein's theory of gravity beyond Newton's theory of gravity, which obviously we're not going to get into here. But I think Herr was alluding also to Mach's principle. Around the turn of the century, a lot of people, well, I think ever since Newton probably, lots of people have agonized over this. What on earth does it mean that mass plays those two very different roles? And Mach had this lovely idea that maybe the reason for inertial mass, the reason things are hard to accelerate, why can't you just push on something slightly and it accelerates instantly, a fantastic rate. It doesn't because somehow or other it doesn't like to accelerate. Mach's notion was that that's actually a residual effect of the gravitational attraction of all the stars and galaxies that are out there. That if you could somehow or other clear all the clutter out of the universe, and you just had an object here, it would have no inertia at all. You push on it, and boom, it would have infinite acceleration, I guess. But it's just a sort of sluggish effect, a cumulative effect of all the gravity from distant stars and whatnot, that imparts to something a resistance to acceleration. I myself think it's nonsense. Einstein thought he built Mach's principle into the general theory of relativity, but I think most authorities now would say, Einstein might have thought that, but I'm sorry, he just didn't.
But didn't Newton discuss it too? He talked about a pail of water
Yes.
that you spin around.
And what is it that determines the unspinning coordinate system?
Yeah, you take a pail of water, you spin around, there's a little bit of friction, and actually the water is spinning, and it makes this kind of funnel-shaped surface inside a spinning water head. I mean, we'd be able to do it a lot better than Newton.
Right. Did he make that second
I don't
part?
think
I'm not
he
sure.
did. I don't think he did, but somebody did. But
Ah.
he did talk about it, isn't it? Is it named after him?
Yeah, the new
So he must
experiment.
have talked about it.
Right, I always took that to be his way of showing that there is a non-rotating reference.
Reference.
Yeah, that's the one in which the surface of the water is flat. And in any rotating, but rotating with respect to what, then I guess.
And
that-
he knew it was the big stars, but later people started to think about relativity, said, what if there is no Mach's principle, the stars start spinning for some reason?
Yeah.
It's not a frame of reference thing, the stars are really spinning, lots of masses around us are spinning. Will it make the water stand up by using this gravitational attraction? That's the question.
And my answer, let's do this experiment. Get all the stars, everything up there. Get it rotating around, and then we'll hold up a bucket of water and we'll see if the water surface is flat. I think it will be.
Means it, no flat?
Yes.
No, I think.
The man believes in Mach principle.
I believe.
Ha!
I think he could do the calculation.
Where are we? So anyhow, that was a side, just to say, don't be casual about this cancellation of masses. It's really an astonishing thing and leads to great things in physics. Yeah.
What about like with electrical charge?
That's it.
Where the mass is almost like meaningless, where it's so small there's like virtually no inertia.
Like an electron.
Well,
Like 2 electrons like cool.
that's a perfect,
That's a great
perfect contrast to this, the typical situation. If I was talking about the attraction or repulsion of two charges, you know what it is then? It's some constant times the product of the charges, Q1 to Q2 over R squared. The product of the charge, there's Coulomb's law, and I would say that's equal to the mass times the acceleration. But in this case, no cancellation occurs. This is Q and this is M. Totally different properties, and it doesn't surprise us that, you know, something can have a large charge and a small mass, or vice versa. No big deal. They're not linked to each other, and that's kind of what you would have expected. Coulomb's law telling you force between charges seems to be utterly unrelated to, charge has nothing to do with inertia in that case. What's amazing in the case of gravitation is that same number m goes in there that goes in here. And therefore there's this opportunity for an astonishing cancellation that would never happen in the charge case. There's a separate property charge. And for gravity, there should, damn it, have been a separate property, mass. No, I can't say mass. There should have been a separate property, what should we call it? Gravitational mass is the word that's usually used in business.
Better yet, gravitational charge.
Gravitational charge, how about that? Yeah, we call it gravitational charge, and we use the letter Q for it, and there's never any cancellation in there. But it just so happens that it's exactly the same number, and it does cancel out. That's why ultimately, all objects in this room accelerate downward with the same acceleration. You know, the old Galileo thing of dropping stuff off the Tower of Pisa, whether he ever did it or not, is a different question. But in principle, two different objects, completely different masses, would land at the ground at exactly the same time because they accelerate modulo air resistance exactly the same way. The Greeks said, how on earth they could have believed this, since it's obviously not true, that the heavier object, of course, falls faster. Where are we? Okay, I was going to do an example of planetary motion using that formula there to calculate the period of the orbit of the moon, a very useful thing to be able to calculate. Don't you think? Well, tell me now, what is the period of the moon's orbit? It's about a month, right? I mean, that's what a month is essentially, but let's pretend we didn't know that. The period of the moon's orbit. Well, what is the speed of the moon in orbit? Well, the speed is the distance it has to go in one full orbit. That would be the circumference of the orbit, 2 pi r, right? divided by t, the thing we're looking for, the period. So V would be 2 pi r over t, isn't that right? Yes. Let's put that into the planetary equation here. I would get 2 pi squared times r squared over t squared is equal to gm over r. I'm going to solve this for t. So let me get the t's onto one side. T squared is equal to 2 pi squared. On the other side, there's an r squared there, but another one from down there, so it's going to be r cubed all told, divided by gm. Nasty. T is equal to 2 pi, I'm taking the square root now, r cubed over gm. So there's another way of rewriting the planetary equation, not in terms of speed now, but in terms of the orbital period and the radius of the orbit. What are the various numbers that go in here for calculating the period? R, the radius of the orbit, or the distance to the moon from the Earth. I've got that here somewhere. Moon. Radius of orbit, 3.84 times 10 to the 8th meters. Yep. Okay, gm. M. What is m here? Ooh.
Mass of Earth?
Mass of the Earth. Not the mass of the moon. That canceled out. Doesn't matter what the mass of the moon is. Any object that was orbiting the Earth up at that same distance would have exactly the same orbital period. But this is the mass of the Earth. That does matter. M equals mass of Earth. And that, according to this, is mass of Earth, 5.97 times 10 to the 24th. Kilograms. T then is equal to 2 pi times the square root of r cubed. Bad mistake, isn't it? R cubed there. 3.84 times 10 to the 8th cubed over g, that was your 6.61 times 10 to the minus 11 times m, that's 5.97 times 10 to the 24 kilograms equals, I was going to put in the actual numbers and use my calculator. Oh, why don't I put it in? Let's see. Ah, shit, this calculator doesn't have a unit function on it. It comes out 300,000 something or other seconds equals 27.3 days. That was cool. Actually, you can do that in your head.
Oh yeah.
Yeah, 27.3. I had to divide the answer. This was coming out in seconds, of course, so I had to divide by 24 to make it down to hours, and then 60 and 60 again to bring it down to days. So 24 times 60 times 60, I had to divide through 5 to get it to days. Actually, honest to God, folks, I did that calculation, and that's what it comes out as. Usually. My calculator at home does have a cubing button. I made it a little easier.
Now see, I'm always confused because the mass of the moon is a little bit more important compared to the Earth than the mass of the Earth compared to the Sun.
True.
And you said something about that.
So, like, you know, I guess if you use reduced mass here,
You know, reduced mass drops out.
oh,
The sum of the masses goes into the formula, but the radius is the reduced radius.
whoa, I guess that's right. But I believe that the center of mass of the Earth moon system is actually inside the Earth.
It is, right?
So, not quite exactly right, but pretty damn close. I think we're on the right track. Okay, now we come back to the question that somebody raised at the very beginning. Is universal gravitation responsible for little g, for the acceleration of gravity on the surface of the Earth? Indeed it is, of course. But why is this problematic? Why are we attracted downward? Well, it's the gravitational attraction of the Earth that's right underneath us. But think about the problem here. This is not trivial. Here I am, mass m, sitting on the surface of the Earth. I am attracted. Thank you. I am attracted right around here toward the north by Mount Washington, toward the south by an iceberg that's floating off Antarctica, toward the center of the Earth by the molten core of the Earth, toward Australia, which is down here somewhere, by a kangaroo that's running around. Each one of these is exerting a gravitational force on me, right? And those objects are all at completely different distances away. They're not all in the same direction even. This one is attracting me down that way. This is the iceberg, it's attracting me like that. The kangaroo is attracting me over there. And something or other else, the Eiffel Tower or so is attracting. I'm being pulled every which way. What I need to do, actually, to do this calculation, is I need to chop the Earth conceptually at least, up into every rock and dirt cloud that makes the whole thing up, each little tiny piece. Calculate the gravitational force of each one using Newton's law of universal gravitation, and then add them all up. Add them all up, moreover, noticing that they're all at various different distances away, and those forces are pointing in different directions. So I'm going to have to take vector components out and add them as vectors. This problem is a nightmare. I don't propose to do it. Not today. You will see the calculation if you take a course at about the junior level, either in electrodynamics or in classical mechanics, maybe both. The famous calculation of that. Take a spherical object, integrate over the entire thing the net force of all the different bits and pieces that go to make it up, and find out what the net answer is. Maybe even next semester you will see an absolutely lovely way to avoid the integral using something called Gauss's law, which was not accessible to Newton, came much later, but there is a beautiful way of avoiding that horrible integral. All I want to say to you now is this is not a trivial problem. This is a deep, complicated problem. In fact, it's a problem that held up the publication of Principia, Newton's book, for 10 years, as I understand it, because Newton was able to do the calculation using calculus. But of course nobody was going to believe that because he just invented the calculus. So he needed to give what was then considered an acceptable argument, which is to say a geometrical argument for it. And he struggled and never did find, as I understand, never did find an acceptable geometrical argument for the astonishingly simple conclusion that I am about to reveal. Newton proved that if you've got a spherical object and you're outside it, it functions gravitationally as though you put all that mass right at the center. What could be more perfectly simple than that? It's just as though you collapsed all that stuff and stuck it right at the center and then apply Newton's law of universal gravitation for that. That's only true for a spherical object. Don't try doing it for cubes. It's simply false then. For a cube, you've got a nasty and irreducibly nasty problem. But for spheres, it's as though you concentrated all the mass at the center. An amazing conclusion that comes at the end of this long calculation. I actually have it in my mind very much right now because I did that calculation in the electrical context. What is the force due to a an electrically charged sphere in my non-Holyoke course about 2 weeks ago. It took the entire hour and a half lecture to do the calculation, and I think it's fair to say that nobody in the class understood it. In fact, I know that nobody in the class understood it because I then assigned exactly that same problem I had done on the homework and nobody got it right. So this is not an easy problem, just trying to reinforce. A lot of people will tell you, well, it's obvious, just concentrated all at the center. That's not obvious at all. It's very deep and very difficult. Spherical object. Thank goodness, however, that makes life a whole lot easier for us. I can now in particular calculate what is the force on me here due to all those bits and pieces that go to make up the Earth. Namely, I just pretend that all of the mass of the Earth was concentrated at the very center. So, the force on an object near the surface of the Earth is G, mass of the Earth, mass of the object in question, that's B, divided by how far away the Earth is. Effectively, it is the distance to the center of the Earth, right? That's what this theorem says. Pretend that all of the mass of the Earth was concentrated at the center. GMM over R squared is equal to my mass times my acceleration. Whoops. I said G. That was right, as a matter of fact. My acceleration is precisely what we call G. Right? Well, once again, this miraculous cancellation of the m's takes place, and I get G is equal to G, the acceleration of gravity, the constant of gravitation, and divided by R squared, the square of the radius of the Earth. This time I really will calculate it before your very eyes. 6.67 times 10 to the minus 11 times the mass of the Earth, which was 5.97 times 10 to the 24th kilograms. And I divide it by, the square of the Earth's radius now. Radius of the Earth is 6.38 times 10 to the 6th. And this should come out in meters per second. Whoops, squared. Meant you. Okay. 6.67 times 10 to the 11 minus 11 times 5.97 times 10 to the 24th. Divide that by 6.38 times 10 to the 6th, and divide it again by 6.38 times 10 to the 6th. And the answer is, I have not looked at this,
9.782.
9.782. Not too bad, huh? 9.78 meters per second squared. That's the acceleration of gravity. What is it from? It's from the attraction of the Earth, all those bits and pieces in the Earth, but functioning as though all of them were concentrated at the very center. I have one last comment for you, by the way, about Newton's law of universal gravitation. Let me write it back here again. M1, M2 over R squared. That actually, in the first instance, is the force on M2 due to M1. And that points, of course, back toward M1. what is the force on M1 due to M2? Well, it'd be exactly the same, only I'm writing them 1 and 2 in the other order, isn't that right? And of course, because it's always attractive, it would be pointing in that direction. That's the force on 1 due to 2, according to Newton's law of universal gravitation. Does this remind you of something? The R, of course, distance between them is the same no matter which one you're looking at. It's the fact that the force on 2 due to 1 is exactly the same in magnitude, and of course opposite in direction, as the force of 1 on 2. Huh, sounds like Newton's third law. Yep, both of them came from Newton. He built Newton's third law into the law of gravity. I mean, he didn't do it. The law of gravity actually contains the third law in this, for the case of gravitational forces, is built into it. If that had not been the case, of course, Newton would have been in serious trouble because the two laws would have been inconsistent. The third law is actually built into Newton's law of